Welcome to this video series on frequently asked questions about the Java language. In this ongoing series of videos, we'll answer commonly asked questions about the Java language. You'll come away from the video with a solution to a question that you as a developer may have. In fact, these questions have been asked by thousands of developers, so you're not alone. Our approach to every question is simple. First, we pose the question about the Java language, Java development, or best practices. Then we fill in any background material so the question makes sense. Next, we'll get into the details of the question and discuss it further. Then we'll come up with an answer. As a bonus, we'll go deeper on the answer and look at a code sample showing you what to do and in some cases what not to do with a counterexample. Stick around until the end of every video where we'll discuss the solution from an application security point of view. We'll let you know what to watch out for to ensure your code stays secure. For more videos like this, please like and subscribe to be among the first to know when we release something new. Ready to get started? Let's go. The question today is, what is the difference between the access control modifiers in Java? Java provides access modifiers to control access to fields, methods, and classes. The keywords, which are also reserved words, are public, protected, and private. And the default modifier, which here is listed as no modifier. No modifier is not a modifier per se, it's simply the lack of an explicit public, protected, or private modifier, resulting in a default modifier. In the coding section coming up, we'll go deep on each one and demonstrate in code all the different levels of access each modifier provides. But before that, let's take a look at each of the modifiers, and later we'll compare them in a table side by side. First, let's look at public. A class may be declared public, meaning it's visible to any class anywhere within an application that uses the class. And at the member level, and here member means a method or field within a class, public means any code from any location has access. Public access should be used with care, since it exposes access to the world. We'll discuss this topic in more detail when we cover the security aspects of access control later in the video. Package private is not a modifier we express explicitly. Rather, it's an implicit modifier when no modifier is explicitly stated. If there's no modifier, such as public, private, or protected, then package private rules come into play. Classes can be public or package private only. If a class has no access modifier, then the class is only visible within its own package. Member level, meaning methods or fields, package private means that these members can only be seen within their own package. Because package private is confusing and possibly misunderstood, it's always recommended that an explicit modifier is used. Next up is the private access modifier. The private access modifier is allowed only at the member level and not at the class level. Private access means that members, once again fields and methods, can only be accessed within their own class. The private access modifier should be used in most cases for member level fields to prevent unintentional or malicious modifications to the data. Finally, there's the protected access modifier. This access modifier is allowed at the member field. The protected modifier allows members to be accessed from within the current class as well as by subclasses in another package. While useful, protected, much like package private, can be confusing, misunderstood, and result in unintended access. Confusing code is antithetical to secure coding. Using either private or public is clear and easily understood and should be used in most cases. Here we see a chart of the different access combinations. The access modifiers are listed in the left column, and the locations where they may be accessible from are listed along the top row. The green check marks represent where access is allowed. The red X's indicate where access is prevented by the access modifier and code location combinations. Starting on the left, we see that public, protected, no modifier, or package private, and private are all accessible within the same class. The next column is package. Here we see the modifier private prevents access to a member field or method within the same package, while all other access is allowed. Next, when subclassing within the same package, the result is the same, only private members are not accessible. For subclasses of a class in a different package, with private or no modifier specified, access is not allowed, while public and protected is allowed. Finally, for classes that are not subclasses and in different packages, in this case, we'll call it the world, access is only allowed through the public access modifier. Now let's jump into the coding section and demonstrate all the access levels that we just saw in the table to bring the points home. Here we are in IntelliJ IDEA, running in Windows 10 environment. Let's start by creating a package. We'll call it com.beginsecure.vehicle. Let's create a class called vehicle. And let's add some class level fields. First, we'll add a Boolean called electric with an access modifier of public. Next, we'll create a variable called primary color with type color and no modifier. Notice that we'll need to add the import statement for java.awt for the color class. Next, we'll add a protected field of type int called number of doors. And finally, we'll add a private field of type int called number of wheels. So we have a member field of each type: public, protected, private, and package private. Let's generate a constructor for our vehicle class. To do this, we'll go up to Code, select Generate, Constructor, and select all of the data fields to be included as arguments to the constructor. Now let's use IntelliJ to generate a toString method. Go back to Code, Generate, and select toString. Once again, we'll select all the fields. Now let's create a main method to run our code. We'll use the PSVM shortcut to create our main method. Then we'll create a variable called vehicle of type vehicle. And we'll pass in some values to initialize the class. We'll say electric is true, color is orange, the number of doors is 4, and the number of wheels is 4. And let's print that out using system out println. Using the SOUF shortcut, we'll create our statement and pass in vehicle, which will invoke the toString method to see our output. Let's run that code, and we'll see our results that we entered echoed back to us. Notice the color is specified using the RGB values rather than the word orange. So far, no big deal. We created a class, initialized it, and printed the values out. Now let's start exploring the limits the access modifiers impose on us. We'll start by changing the fields of the vehicle object. Since we're in the same class, there should be no restrictions on anything that we change. So if you recall from our table, this is the row of all green checkboxes. So let's start by setting electric to false. Color to black. Door count to 1. The number of wheels to 2. And print out the values of our changed vehicle. When we do, we see that all the fields have changed, so there's no limit on what we could do within the same class, regardless of the access modifier. Now let's create a new class called Vehicle Test. We'll create it within the same package as our vehicle class. Once again, we use the PSVM shortcut to create our main method. And we'll create an instance of our vehicle class once again. Our variable will be called vehicle. And let's assign it some values. Electric is true. Color is black. Doors and wheels are 4. Add a println statement and print that out. And run the code. When we do, we see that we get the results printed out. Notice here that black has an RGB value of 000. Now let's modify the fields in the vehicle object we created. We'll set electric to false, primary color to red, number of doors to 5, and if you notice in the drop-down of available methods and data fields that IntelliJ provides, there's no reference to the field number of wheels. Recall that we made the number of wheels private in our code, so it won't be available to us here to modify. Although we're in the same package, we're in a different class, so private is not available to us to modify. Let's go ahead and print out the results. We see that all the data fields changed, except the number of wheels. Now let's create another class. We'll call it motorcycle. And let's extend vehicle, so our vehicle is a superclass and motorcycle is a subclass of the vehicle class. And notice too that we're in the same package as before, namely com.beginSecure.vehicle. We'll use IntelliJ to generate our constructor, which will invoke the constructor of the vehicle using super. Now let's create a method called override. And here we'll attempt to override whatever values are set in the data fields in the vehicle superclass. We'll set electric to true, primary color to orange, number of doors to 5. And when we try to change the number of wheels, once again we see that it's not available to us to change. Here we're illustrating the third column of our table. When we have the condition of a subclass in the same package, we don't have access to modify private fields. Moving on, let's now create a new package. We'll call it com.beginSecure.autos. And in the autos package, we'll create a class called car. And we'll extend the vehicle class. Once again, we'll let IntelliJ create our constructor. This time we'll use the PSVM shortcut to add our main method. And we'll create a variable called car of type car. And initialize it like we've seen before. And then print those values out with a print line statement. And then we'll run the code to see the results. Now let's try to change the fields in the car class, which is extending the vehicle class. First, we'll set electric to false, and the number of doors to 2. Notice that primary color is not available now for us to modify. Recall that primary color had no modifier, or as it's known, it was package default. Because we're in a subclass that is outside of the package containing the vehicle class, we can no longer modify this field. This is represented by column 4 in our table. If we print out the value of the modified car, we see that only the data we had access to was modified, while the others retain the original value from the invocation of the constructor. One last time, let's create a new class called Global Vehicle Test. Notice we're creating it in a package called com.beginSecure. And let's use PSVM to create our main method. Once again, we'll create an object vehicle of type vehicle and assign it our 4 favorite values. And print the results. Now if we try to change the fields, we see that only electric is available to us. This illustrates the 5th column in our table, in which a class that is outside of the package where the class exists and not a subclass will have access only to the public fields. Let's finish things off by setting electric to false, adding a print line, and running the code. As we've seen, the only value that we were able to modify is changed, while all the other values from our constructor invocation remain the same. Now let's look at security concerns around Java access modifiers. First of all, are there any security concerns? Yes, there certainly are. If an application doesn't properly protect data that's assumed to be immutable, that is, data which cannot be changed, from being modified by a user, whether intentionally or by accident, it can modify the application behavior in unexpected and potentially dangerous ways. Even the use of final is not always sufficient to protect the data. Malicious code from another package may change data if the access modifiers are not set properly in your code. There are many CWEs related to this topic. They include 607, Public Static Final Field Reference Mutable Object, 471, Modification of Assumed Immutable Data, 766, Critical Data Element Declared Public, 496, Public Data Assigned to Private Array-Typed Field, and many more. Careful attention to these CWEs is especially important when writing library code used by your team or others. The developers working on any open source project should pay special attention. Unfortunately, these vulnerabilities are often regarded as noise, or in some cases even false positives, by many static analysis tools or security teams. Pay attention to these findings. Although they may be characterized as low-risk findings, a determined attacker can manipulate your code in unexpected ways, resulting in a compromise of your system, or the compromise of systems that use your code in the case of third-party libraries you supply to others. Thanks for watching. We hope you enjoyed this video. Please like, subscribe, and share this video with others. Right now, while it's still available, go to www.beginsecuretraining.com to get our free ebook on how to write more secure Java code. When writing code, remember to always begin secure.